Okay, hi everyone. Welcome back. So let's continue from where we were last week. So last week, if you remember, we started talking about light, and we were making our way towards a model of some quantum computer using photons. But for that, we started discussing electromagnetic fields, and we saw how a single mode of an electromagnetic field is basically a quantized harmonic oscillator. So we discussed that. So a harmonic oscillator, which will have these energy levels. So you can imagine, an electromagnetic cavity with a mode trapped inside, and it can be a single mode cavity. Just imagine a single mode for now. So then a single mode in that would have energy level spacings of h bar omega, and we introduced the Fock bases, or the number bases, where the n, which is the photon number state, was basically a dagger to the power of n applied on the vacuum, which is 0, over n factorial. And we also introduced the lowering and raising operator. So A operating on n gave us square root of n minus 1, and A dagger operating on n gave us square root n plus 1 n plus 1. And we also specifically wrote that a single photon would just be applying a dagger once on the vacuum state. The second thing that I started introducing, so that was the single photon state, right? So we had single photon. We said that a single photon is just a dagger on the vacuum. And then the second thing that we started talking about was the coherent state. Okay, good. Sorry. And the coherent state, where was that? The coherent state, we'll learn why it's important in just a second, but the coherent state is defined, if you remember, as the operator A operating on some coherent state alpha. So some coherent state alpha, this would be coherent state. Alpha, remember, is a complex number. And when A operates on alpha, we get alpha, alpha. Okay, meaning that alpha, the coherent state, is an eigenstate of the annihilation operator. That's what we did last time. And also using a self-consistent equation, we calculated what is alpha in the Fock bases. And we saw that alpha in the Fock bases was e to the minus alpha squared over 2. This was the normalization factor. And we saw that it is a sum, basically a superposition of many Fock states, alpha to the power of n, square root of n. Now what we're going to see now, I'm going to talk a little bit about the properties of the coherent state. And what we're going to see now is basically that the coherent state is a state which is the closest thing to a classical field. Okay, so up until now, when we're talking about electromagnetic fields, we were just talking about a simple sine wave. That's all you can do. You can take something and sinusoidally drive it. We'll see that this coherent state, as the state gets bigger and bigger, meaning more and more photons in this state, it approaches a classical state, and then we will understand why this is very important for quantum computation. Okay. And after we do that, we'll go back to the single photon and we'll build like a single photon model. So what we're going to do now is we're going to discuss properties of the coherent state. And before I do that, I just forgot that I did not switch off my phone. So I will do that. Sorry. Okay. Okay, so the first thing you can see from the coherent state, maybe I'll write it down up here again, just so you have it on the same board. So alpha is e to the minus alpha squared over 2, sum over n, alpha to the power of n, divided by n factorial n. So this is the coherent state. And the first thing that you see about the coherent state is that the probability to measure some n, so suppose that you're asking what is the probability to have n number of photons in the state, that comes out to be e to the minus alpha squared, alpha to the power of 2n, n factorial. And this is familiar to you. What is this distribution called?
Poisson.
Exactly. This is a Poisson. It's a Poisson distribution. So if you look at the state alpha, this is the probability of some n. This is n, the number state. Then you will have something like this, distribution, where these bars, indicate photon numbers. The second property refers to the average photon number. And the average photon number, this can be easily calculated. We do alpha. We apply a dagger A and calculate the average. This is the number operator. So it counts the number of photons that you have in a state. Okay, and we're applying this with respect to the state alpha. This calculation is pretty simple. You just apply A on alpha here, so you get alpha. And a dagger you can just apply backwards. So you get alpha star, which means that you get alpha squared. So the average photon number is alpha squared. You can think of it as the energy in the field. It's proportional to the energy that you have in the field, the average photon number. If you calculate the variance, so delta n squared, which is just n squared minus the average of n squared, this will also be n. So the average photon number is alpha squared, but also the variance is n squared. And another nice property to remember is that this is what is called the minimum uncertainty state. Minimum uncertainty state just means that if we calculate delta Q, delta P, remember last week we defined delta Q as the position operator, and delta P was the momentum operator for the electromagnetic field. I gave you the explicit expressions in terms of the raising and lowering operators. And if you calculate this, you will get h bar over 2. And you could calculate this simply the same way that we calculated this. So delta p would be square root of p squared minus p squared. Okay, so you can do this calculation for p, for q. It's a simple exercise, and you will get this minimum uncertainty state. It means that if you draw some phase space for this, then the uncertainty will be as minimal as possible for this type of state.
Can I ask a question?
Yes.
How did you get to in property number 3?
Yes.
How did you do average of n in the end?
How did I get? Oh, I didn't. You take n squared, so you got to calculate. So just like I calculated n bar here, you calculate this. So you have alpha. You have a dagger a dagger a.
Yes.
Okay. That's n squared.
Okay.
And then you just plug it in, and you do the same for p and q if you want to do this.
Okay. Thank you.
Okay. There you go. Now the fifth property is maybe the most important and most relevant for us. I'll write it here in the next board. So number 5 looks at what happens for the state for large alpha, meaning alpha much larger than 1. Okay, so we have large amplitudes. Okay, now think about it. This alpha thing. If you want to equate this thing to a regular harmonic oscillator, alpha is basically your amplitude of oscillation. Okay, or the magnitude of alpha is the magnitude of your oscillation. The phase of alpha is just going to be the phase of your oscillation for a classical oscillator. A quantum one will of course have the uncertainty that goes with it, the uncertainty for x and p. Now if we look at large alphas, okay, so a very large average photon number, what we're going to see is that it is a classical field. Okay? Now, meaning you just get a sine wave. Now, how do you see that? Well, to see that, basically what you want to do, remember, if you take the electric field operator that I gave you last time, remember, E was proportional to A dagger minus A. It has the exponentials with omega t and everything and all that, but you can apply that to a coherent state. So first thing you want to do, you just apply E to a coherent state. The second thing you want to do is, so we know what A does to a coherent state. We get alpha back. But now we want to take the limit where alpha is much larger than 1. And let's see what happens when we apply A dagger onto alpha. Again, in this limit. So when we apply A dagger to this alpha, we get e to the minus. Oh wait, we're not applying the limit yet. 2 sum over n. So now I'm just operating with A dagger on alpha. Alpha to the power of n, square root of n factorial, n plus 1, n plus 1. So this is what happens when you apply A dagger. If you take this limit, you can see that's what's written here is basically, what is this? It's just alpha itself, or proportional to alpha, basically. Okay. For very large n's, n, you can think of it as for very, very large n's, n and n plus 1 are practically the same thing. Okay, if you think about it in terms of distribution, so you have the distribution, let's say, for alpha, for state alpha, and the distribution for, maybe I'll take another pen. And this would be the distribution for a dagger on alpha. They're practically the same. Again, this is for alpha much larger than 1. And this is important. It means that if you have this field, a coherent field, and you remove a photon or add a photon, you get the same field. The field is practically unchanged. Now this has very, very large significance in general for quantum control. Okay, so this is, and I'll explain why. So this is important for quantum control. So let's go back to what I want to do. Go back now to the model of a two-level system. Okay, so think of the model of a two-level system. And think of this two-level system which you want to control. You want to excite it. So go back to the NMR. How do we excite a two-level system with NMR or with a classical electric field? What do? Anyone? 0, 1. How do we get it from 0 to 1 and backwards and so on? What do we apply?
You apply a magnetic field.
A magnetic field, that's right. A rotating magnetic field if it's NMR, an electromagnetic field if it's an electric dipole. And the frequency of this field, right, is at omega. Okay, meaning that the photons that we're sending, the energy of each photon is h bar omega. So this is the energy difference, right? We're sending photons at the Larmor frequency of the magnetic spin. Now suppose that you have this two-level system with h bar omega, one of them, and it's situated right here in space. There it is. And now you send a single photon packet. What would happen if I send a single photon packet at h bar omega? If my two-level system is in the ground state, it will absorb the photon and go to the excited state. If my system is in the excited state, what happens? You get?
Spontaneous emission.
You get emission. Stimulated emission, you wanted to say.
Yeah, stimulated.
Yeah.
Sorry.
Yeah. You get emission, right? Basically, the photon comes along, and then you get two photons being absorbed, and you get the transition from here to here. Okay? Now, think about the following situation where you're trying to control this two-level system. This two-level system is a qubit. And you want to do a coherent operation. You want to move it from 1 to 0, from 0 to 1. You want to do an X operation on it. But you don't want in the environment to know, because if the environment can detect what the state was, you lost all your coherence. The environment collapsed the state. Now think about the situation where, again, this is a Gedanken experiment, but we put many, many detectors here. All over, all around the system, we put as many detectors as we want, all around, such that the chances of missing photons that are being scattered from this atom are practically nothing. This means that I don't know, initially I don't know the state of this thing, but now I send in the single photon. Now if I send the single photon, I can later detect If I detect no clicks on any of the detectors, I know that my atom was in the ground state and now it's in the excited state. If I detect 2 photons, right, I know that it was in the excited state, not in the ground state. It means that I have lost my ability to control the system without knowing what I did. Okay? But here comes the importance of the coherent state. If now instead of sending single photons to do this control, I'm sending a large superposition of many photons, a state where in the very large photon limit cannot distinguish between ground and excited, even if I have perfect detection efficiency, then I regain my ability to do control without the environment knowing. You can see this from the overlapping distributions, right? The 2 overlapping distributions is where the information is encoded. And because the 2 distributions alpha, which is what happens if you lose a photon from alpha, and A dagger alpha, which is what happens if you add a photon to the field, because the distributions are practically overlapping, the wave functions are practically the same, then the environment cannot detect what has happened. And you regain the coherence that is in the system. Now, in terms of quantum computation, this is one of the first problems that physicists were thinking about when trying to conceive of systems that you would realize quantum computation on. This was one of the very first problems, and very quickly they realized that when you have a classical field to drive this atom, you don't even run into this problem. Okay, and this is the importance of the coherent state in the context of quantum computation. Are there any questions about this?
Can you please emphasize where we use the fact that alpha is much greater than 1 on the top expression at the number 2?
Here. Basically here you have n plus 1 and you have n plus 1 over here. If alpha, remember alpha, okay, alpha squared is n bar. What this means, see, this is just what this, whereas the distribution is written over there, but this is kind of the square root of the distribution. If you think of it as a Poisson distribution, and as you go to larger and larger numbers, it becomes a Gaussian, and a Gaussian that is very broad. The width of the Gaussian is n bar, okay, and if I have 2 broad Gaussians and the difference between them is in n, as n becomes larger and larger, the difference is going to become smaller. Okay, it's going to become exponentially smaller. Okay, and you can see it here basically. If you take this, if you plug in 2 small numbers, you'll get a bigger difference in the distribution. What you can do, if you want to do this a bit more rigorously, you can take this state and overlap it with alpha, and then calculate the difference in the projection. Okay, so take, let's say, fidelity merit between A dagger alpha and alpha, and then calculate the fidelity between them as alpha becomes larger and larger. Okay?
Okay, thanks.
But basically, you can think of it, see, this is a sum of these things. And these are the amplitudes. As n becomes bigger, then this sum for n is going to be just, you're going to have basically the same components of the wave function for larger n's. Okay? Any other questions? But it's a nice exercise that you can do to calculate explicitly the fidelity as function of alpha between A dagger alpha and alpha itself. Okay, so if there are no more questions, we'll now move on from the coherent state, and we'll move to constructing, well, basically a primer for an optical quantum computer. that uses photons. So the discussion that I'm going to give you now is following the discussion that you can find in Nielsen and Chuang. So we're going to look at a single photon model for quantum computer. Now this is a simplified single photon model. We're going to go through the basics of this model just so you get the idea. When people talk about photonic quantum computers today, this is not what they're talking about. They're talking about more advanced ideas, and you're going to realize when we go through this model why. Because this model has many problems which are just too difficult to overcome, and we're going to understand those. And at the end, I'll mention a little bit about what these more advanced models are, and that's it. Okay. So just to be explicit, I'm following Nielsen and Chuang, their discussion over there. Now for a single photon model, so suppose that you want to construct a quantum computer using a qubit made of a single photon, the simplest choice for 0 and 1 are? Anyone?
Polarization.
Polarization. That's more complicated. Polarization is actually the preferred choice for the KLM scheme that I will mention later. It is a more advanced scheme. We're not going to discuss it. If we have time, it's in my notes, but it's saved all the way to the end of the course. So we're going to do this model, then we're going to do the other technologies, and then at the end, if we have time, I'll talk to you about the KLM model for linear optics and maybe the measurement-based quantum computation, which is even more advanced than that. Okay? So no, not the polarization. The simplest thing is to take, but you're right, in a sense, the polarization is more simple. To take 0 as being no photon and 1 being just a photon. Okay, so 0 and 1, photon. And this first step, even this very simple first step, has a problem with it, which is easy to circumvent, but I'm just introducing it to show the problem with it. The first one is loss. If you lose a photon, then you don't know. You always measure nothing. You don't know if you lost your qubit or it just flipped from 1 to 0. But you can overcome that. So the first problem is loss, but it's not a big problem. So problems. The second one is the problem of phase shift. The problem of phase shift is even more annoying because if you think of this photon and it's traveling in this fiber, it's picking up a phase as it is traveling through space. Okay? It means that the length of the fiber, you have to keep track of the length of the fiber to an incredible accuracy to track the phase of this qubit, which poses a really big problem. The way to solve this is using what is called a dual rail qubit. And this is the model that we're going to discuss now. Okay, the model of a dual rail qubit. And the dual rail qubit solved these two problems using the following encoding. So your 0 state is going to be encoded into 2 modes. You can think of 2 fibers or 2 modes inside the same fiber. Okay, but think of two fibers. It makes it maybe simpler to imagine the things that we're going to describe now. And the 0, 1 here is basically for mode A and mode B. So we have two electromagnetic modes, two quantum harmonic oscillators, A, that we use A and A dagger to describe, and B, which will be B and B dagger. And our 0 logical will be 0 and A and a single photon in mode B. And the 1 logical will be this thing. Okay? And we have, and so A and B are two electromagnetic modes.
Why do we care about the phase? Why is it a problem that we have phase shift? We don't use the phase for the qubit. It's just a photon or no photon.
Oh, no. There is a phase. When you write a qubit, you have psi, and you have alpha 0 plus beta 1, right? Take out, renormalize it. You can just write it as e to the I phi, right? This is your qubit.
Okay.
And now this phase is propagating.
Yeah.
Okay, so basically as it's propagating, you're getting these rotations around Z. And now you have the extra overhead, which you have to now keep track of these rotations around Z. Okay? It's not it doesn't kill you. You can handle it in ways. But a nicer model is to use this thing because I'm going to show it right explicitly on the board in just a second. When these two things propagate in time, they're going to be picking up the same phase. Okay, so you won't get this phase shift. So what we're going to do now, on the board, I'm going to show you that using... So what we're going to do now, I'm going to show you that using simple components, I'll write down what these components are. We get single qubit control. So you can think of an optical table with fibers and you place your things and you can control a single qubit for now. Later we'll talk about interacting qubits and we'll talk about the big problems there. But the simple components that you need for this are one, a phase shifter. And a phase shifter in optics is just some material with a refraction index larger than 1. What it does, it slows down the propagation of the phase, and then it causes phase accumulation. And it's pretty simple. You just put pieces of glass there, or something that has, maybe something more substantial than glass. The second thing is a beam splitter. Which the microwave version we saw, that was the directional coupler in the NMR system. In optics, a beam splitter is basically a mirror, a partially transmitting mirror. And the third one, I don't know why I wrote it was 1, 2, and 3, is a mirror. But I guess a mirror is just a beam splitter where the ratio between transmitting and reflecting is 1. So. But with these three things, we basically get full control of a qubit. So this is what I'm going to show you. So this is what we're going to do right now. Are there any questions about this? What we're going to do, what I'm planning to do, what the idea is, and what the model is?
You wrote a third thing down there. I can't see it. If you
Where? Here.
There's a third thing, or
This is a
no? And there's 1, 2. The screen is little is 2. The words too much. Now I see it.
what are you referring to?
What the third one?
Third one.
Mirror.
Mirror. Yeah, I wrote here a mirror. You don't really have to write a mirror, like I said. You can put mirror inside beam splitter, really. Okay, a mirror and a beam splitter are the same. Just the mirror is a beam splitter that transmits nothing. Everything is reflected. We'll write the explicit model for a beam splitter, the quantum model for a beam splitter, as we do the derivation. Okay, but this is the plan. I just want to make sure that everybody understands the plan and what we're going to derive and why. Okay, so this is our qubit encoding, and with these we're going to show control, just control. I'm not talking about how to create the qubits, and I'm not talking about how to measure the qubits right now. Okay, so let's look at these components and see how they give us control over this thing. Okay, so the first thing we're going to do is we're going to see how a phase shifter as you could have guessed gives us Z control. I mean, in a sense, we took that degree of freedom away when we moved to the dual rail qubit, but we do want to gain that control. Okay, so we do want phase shifts. We just want it to be under our control. And as I said before, if the one state of your qubit, as time goes by, is going to accumulate e to the I omega t. Okay, so this is when time goes by. And this is going to happen on all the modes the same. This is why we don't acquire the phase shift in the dual rail. If we now add some material, we have the time plus whatever this material adds for us. So it will add some kind of phi. So we're going to have e to the I omega t plus some phi. And this is what we want. Okay. So for our qubit, I'm going to write explicitly what we get for our qubit. Our qubit has two rails, so this is rail A. So this symbolizes the mode A. And the mode A, what we're going to do is we're going to put a phase shifting material. So n is going to be larger than 1 for this phase shifting material. And for mode B, what we're going to do is nothing. And then if you write what happens to the logical states, so the logical state 0, 1, nothing happens to 0, 1, it just stays 0 and 1, because 0 maps to 0 and 1 on mode B maps to 1 on mode B. But the one logical state, which is 1 and 0, this will map to e to the I phi 1 and 0. If you want, you can write this explicitly as some alpha 0 logical plus beta 1 logical, and this will map to some alpha 0 logical plus beta e to the I phi 1 logical. And if you write this on the block sphere, this is just going to be your block sphere. So this is just going to be a rotation of some phi in the block sphere representing the state space. Okay? So z-axis rotation.
It's also 1L at the end, right?
The
one, it's 1L at the end of the line?
1L, yeah, logical, that's right. It's a logical state, logical state. Okay, so any questions about this phase shifter thing? All right, I can see you're running off to the hardware store to buy pieces of glass to phase shift light. Great. The next thing we want to discuss, so if you're at the hardware store, you're buying some glass to phase shift, buy some partially silvered glass. That will act as your beam splitter. So we're going to do this on the next board over here. We're going to talk about the beam splitter. And we're going to see how a beam splitter allows us to do rotations around x and y, basically, around the other axes of the block sphere. So, 2. Beam splitter. Now, like I said, a beam splitter is basically a partially silvered mirror. It's just a piece of glass that transmits. So the idea is that you're going to have some mode A incoming, and part of the mode will get transmitted.
We're not seeing the board you're currently on.
Oh, you're seeing the wrong board?
Yeah.
אתה יכול להעביר לוח? תודה. Okay, all right. So, okay, so beam splitter, that's a partially silvered mirror. And this partially silvered mirror, we're going to have an incoming mode and the outcoming. And you also have another port, which is mode B here. It's going to be incoming, and there's outcoming. So when A comes into here, part of it will be transmitted, but part of A will also be reflected, right? So mode A will be transmitted and reflected, and mode B over here is going to be reflected in this direction and transmitted in this direction. Now this resembles a little bit, if you remember, the directional coupler which I drew for the microwave, for the NMR setup. So practically it's the same thing. Okay, you have these two cables where you input here light, and the light mostly transmits over here, but some couples out here. And also, if you bring in light from here, it mostly transmits out here, but some gets coupled out here. Okay, so this is the microwave drawing for a beam splitter, where the distance between these two transmission lines, we can think of them as microwave fibers, okay, will determine how much is reflected and how much is transmitted. So infinite distance will be just a mirror. This comes in here and fully gets reflected over here. This comes in here, fully gets reflected over here. And that would be if you take this slab of glass and make it fully opaque. So everything that comes in here gets reflected here, and everything that comes in here gets fully reflected over here. And this thing can be described by a transfer matrix. So this is the electric field A prime, and this is, the electric field B prime, and it's related to the incoming fields by the transmission coefficient and reflection coefficient as function of omega. So this is as function of the frequency. Okay, it can be different for different frequencies. And this is EA, the incoming field, A and B. And this is just a description of the classical behavior. And I think if you took like a linear optics class, a wave class or something like this, you've seen this. And you might have also seen that you can parameterize this with some angle theta. Okay, so you can do some, so this is some unitary that depends on some angle theta. And then you can write this u of theta as cosine theta over 2, I sine theta over 2, there's a minus, no, I sine theta over 2, and cosine theta over 2. So this is the unitary that, well, it's not a, this is the, yeah, this is the unitary operation. Sorry, it's a rotation operation that describes this this matrix over here. All it says is that this thing, this field that's incoming, is going to be split into a reflected part and a transmitted part. Okay, this is all this thing is saying. Also, in general, you can add, because your light is coming in and this is made out of some material. This material has a refractive index which may not necessarily be 1. It means that what's going to happen to this? It's going to add an additional phase shift, exactly, just like a Z rotation. Okay, so you're going to have, in general, some e to the I phi also, e to the I phi coming in here. Okay, but you can ignore this for now. It's not that important. What's important is just to see that the structure of this is a rotation like this. So this is pretty simple. What I'm going to do now is I'm going to give you the quantum version of this thing. So I'm going to give you the Hamiltonian that generates this operation. And I'm going to show you that this Hamiltonian generates a unitary that will give us a rotation in the space of this qubit. Okay, so this is what we're going to do now. And then after we have the quantum version, we'll see how it basically gives us control. Okay. So I'm not deriving a quantum version. I'm just writing. I'm giving you the Hamiltonian. I moved board. Thank you. I'm just going to give you the Hamiltonian, and then I'm going to show you in simple steps how it reproduces the classical result in the limit of a coherent state. Or I'm going to show you the way to do it. You can fill in the math yourselves. Okay? So a quantum beam splitter, or you can call this a quantum description. Maybe description of a quantum description of a beam splitter. Because at the end we want to know on the quantum level, our quantized fields, how this beam splitter is going to affect them. So the Hamiltonian is minus h bar g of t over 2. G is some coupling parameter. It's a parameter that couples A to B. Maybe I'll write here. This, remember, we have A. This is B prime, A prime, and this is B. E to the minus I phi A B dagger plus e to the I phi A dagger B. And what you can see, what this Hamiltonian does, it basically mixes the two modes. It destroys a photon for mode B and creates a photon in mode A, plus the Hermitian conjugate creates a photon in mode B and destroys a photon in mode A. Okay. The unitary, the time evolution of this is just going to be e to the I ht. And what we're going to do is, so I'm going to write this unitary now for this Hamiltonian, but also I'm going to take the extra step of parametrizing G in terms of time, because this whole thing is going to be coming, it's going to be spending some time over here and then being transmitted or reflected. And we don't care about what happens during the time evolution, we care about the whole evolution itself over some time t that the light spends in this beam splitter. So what we're going to do is we're going to define theta, and we're going to call it theta because it's exactly related to the theta that we saw in the previous matrix, and this is just going to be the integral over the time g of t dt. Now, u of theta, in that sense, well, you can add phi here if you want, this phi that, because we also have phi for some additional phase shift. It's going to be e to the minus I theta over 2 e to the I phi A B dagger plus e to the, missing a minus here, I phi A dagger B. So this is the unitary. All I did is just plug this into here and plug that into G over here. And now you can calculate this thing explicitly for A and for B. So we can calculate explicitly Does anyone know how to do this calculation? Use your favorite formula, which is when you have exponentials of some operators sandwiched between operators. Baker, Campbell, Hausdorff formula. Those who don't remember, Wikipedia. Those who do remember, also Wikipedia. Okay? This is one of the most useful formulas for all these calculations. I also mentioned it a couple of, did I mention it? A couple of lectures ago? Maybe not. I don't remember. So yeah, go look on Wikipedia, Baker, Campbell, Hausdorff formula. And using that, you can calculate this explicitly, and you see that A dagger, A, the output field here, is just going to be given, which is U, A, U dagger. And this is where BCH comes in, because U is just an exponential of this, and U dagger is the other one. And you have A here, which is sandwiched in between, which does not commute with A dagger over here. So this is where all this comes in handy. If you do the math, and it's calculating several commutators, but after you do the math for the several commutators, remind you A dagger, B dagger equals 1. Right? You get cosine of theta over 2. A plus e to the I phi, I e to the I phi sine theta over 2 b. And b prime u b u dagger, this is going to be I e to the minus I phi sine theta over 2 a plus cosine theta over 2 b. So this is the result that you should get if you do the calculation. Now at this point, what you can do to regain the classical behavior is plug in. What would you want to plug in? What is classical? We just talked about it. It's a very nice state, which gives us the closest quantum thing there is to a classical state.
The coherent
state. Okay? So if you plug in the coherent state, you will regain the classical matrix, the classical behavior for the field that we saw on the other board over there. So you can already see that this thing is giving us a rotation. So maybe take a 10-minute break now, and then I'll write it down explicitly. I'll show you how this thing allows us to get rotations inside the block sphere. I'll write it explicitly, and then we'll continue from there. So take a 10-minute break.